to evaluate the Fourier series of the absolute value of x, so that it is our function, so f of x is equal to the absolute value of x, and x is between negative pi and pi. So I will again first find my complex Fourier coefficients and then find my real Fourier coefficients using the complex Fourier coefficients. So if I use the complex case first, I have 1 over 2 pi times the integral from negative pi to pi of the absolute value of x, so that is our function, times e to the negative I n x, that is our complex exponential, because here we deal with the complex Fourier coefficients, okay? And so now we can split this absolute value into two parts. From negative pi to 0 it's negative x, okay? And from 0 to pi it is positive, okay? So we have 1 over 2 pi times negative the integral of negative pi to pi of x e to the negative I n x dx plus the integral from 0 to pi of x e to the negative I n x dx. And so now I can switch this negative pi and this 0, and so I will get a minus here, okay? Remember, the integral from a to b is equal to negative the integral from b to a. And so if I already have a negative sign in front here, I will get negative, so positive. So I will get positive the integral from 0 to pi to negative pi of x e to the minus I n x dx plus the integral from 0 to pi times x e to the negative I n x dx. Okay. And so now I use again the tabular method. You can look it up. It is really, I really advise you to look it up. It's really much easier to do integration by parts using that tabular method. So that's what I did here. So I took the derivative of x and integrated this e to the negative I n x. And so finally you should get the result here. So x times e to the negative I n x over negative I n plus e to the negative I n x over n squared, and I have this 1 over 2 pi here in front. And so first I take first my integral boundaries are 0 and negative pi, and then in the second case are 0 and pi. So if I plug in everything, so here from 0 to negative pi and then here from 0 to pi, I get the following. So that's a lot. So I get negative pi times minus 1 to the nth power over negative I n plus negative 1 to the nth power over n squared. So that is my negative pi plugged in, minus 1 over n squared, that is my zeros plugged in, because here I have an x. So if I plug in 0, I get 0, but here I will have 1 over n squared, and because it's in the first boundary, it's negative, okay, remember it's the integral from, we plug in b, and then negative, we plug in a, okay. It's the lower boundary, so the boundary here, and so we put negative in front of everything. I think you should understand what I'm saying, I hope at least. So I have negative 1 over n squared. Now plus I plug in this pi here and get pi times negative 1 to the nth power over negative I n plus negative 1 to the nth power over n squared, and then again minus 1 over n squared, that is the 0 here. Here I get again 0, and here I get negative 1. Okay, I get 1 here, but again it's this boundary here at the bottom, and so we subtract everything. And so now this here and this here cancel, okay, because I have negative here, and here I only have negative, so it cancels out, and you're left with and this term here, that and that. And so I have it both 2 times. In both cases I have it 2 times, so I can factor out the 2, okay? I have this one here and this one here, and this one here and this one here. So I can factor out the 2. And so I'm left with negative 1 to the nth power minus 1 over 2 pi. Okay, this 2 pi here. Just 1 minute. Yeah, and the n squared here. And so this whole thing is 0 if n is even, because if I plug in like 2, I get, yeah, if I plug in like 2, I get 1, so 1 minus 1 is 0, and it's odd if like I plug in 3, it's minus 1, so minus 1, minus 1, so minus 2, yes, and yes, so I get minus 2 over pi n squared, okay, I have a 2 here in the denominator and the 2 here, so it can cancels out, and so yeah, here we're left with the minus 2 in this case, and so we get this minus 2 over pi n squared. And now again, if n is equal to 0, we divide by 0, so we need to evaluate that separately, so we do c sub 0, and yeah, so it's the same thing. We have our absolute value that is split into two cases, whether e to the I nx, e to the negative I nx is 0, so we have simply 1, and so we simply evaluate x basically between negative pi and 0, and then 0 and pi. And again here I have a negative, I can switch the boundaries here to get rid of that negative, and so at the end I evaluate it between 0 and negative pi, and 0 and pi. And so at the end you should get pi over 2 for c sub 0. Now again, the real case, a sub 0 is 2 c sub 0, so it's simply pi. A sub n is cn plus c sub negative n, so I get negative 4 over pi n squared, okay, this here. B sub n is 0, because I have I times cn minus c sub negative n, so if I have that minus that, I get 0. Yes. And so I have my real Fourier series, which is equal to 1/2 a sub 0, so pi over 2, times the sum from n is equal to 1 to infinity of a sub n times cosine nx plus b sub n times sine nx. So this b sub n is 0, and a sub n is this value here, as said, and so we're left with pi over 2 plus the sum from n is equal to 1 to infinity of negative 4 over pi n squared times cosine of nx. And here, remember, n is odd. Okay, so n can be written like 2m minus 1, okay, where m starts at 1, okay. Yes, because as I said, if it is even, we simply get 0. And so we're only left with this pi over 2. But if it's I mean, sorry, no, this pi over 2 is for a sub 0, and 0 is even, so it's what? Okay, I don't know, anyway, for the n, if n is odd and not 0, yeah, we get that result here, and if n is even, we get, and not 0, we get 0 simply, and we have our separate case here where we divide by 0. If we plug in if you use the general formula. Okay, I hope I don't trouble you too much. Just at the end you should get that. And just simply remember that n is odd for the general case. So not for the case where we need to be special, because otherwise we divide by 0. Okay, we do this c sub n because otherwise in the general case, here we have an n squared in the denominator, we divide by 0. And so we need to do this separate case, okay? We cannot simply use the general formula and plug in n is equal to 0. That wouldn't work. Because I said we would divide by 0, so that's why we do this special case. So then, yeah, for the general case, you see that yeah, you have two cases for even and odd. If n is even and not 0, of course, we get simply 0, and then if n is not 0 and odd, we get this minus 2 over pi n squared. Yes, and then you use your real Fourier coefficients. Yes, so the same thing as before. You have your period, you use the tabular method, and you find your complex Fourier coefficients, and then you find your real Fourier coefficients, and you look at the case set where we divide by 0, and you do those cases separately, and then you have your formula here. You plug in everything, and so yeah, I said here in this case, remember n is odd, so it can be written in the form of 2m minus 1, where m begins at 1, okay. So we would have simply, can I write it here? Pi over 2, it's a 2 here, plus the sum from m is equal to 1 to infinity of minus 4 over pi m minus 1 squared, so that's a m minus 1 here, times cosine of m minus 1 times x, 2m minus 1, sorry, 2m and 2m minus 1 here. Okay, I don't think you can really read it. Yes, anyway, you can just replace every n with 2m minus 1. Anyway, yeah, so I hope I didn't disturb you too much in this video. Yeah, thanks for watching.